Good morning. My name's Anne Marie Weaver. If you haven't met me before, I've been with Lightning now for the last 6 years, currently over the engineering and manufacturing things here at Lightning. And we've been doing these webinars. We started doing them during COVID and have kind of picked back up on them. And we think they're, a really good way to connect with our customers. So we appreciate your time. Also with me today is Eno Oliveras, our EMI manager, who developed this low voltage electromagnetic inspection technology. And then LJ Gilliott, our president and COO. So they'll be available at the end for maybe any technical questions that you have. And then any questions, referring to the case study, I'm happy to answer if I'm able to, or if I can't, I'll get in touch with the engineers. So today we'll be presenting on, continuous rod scanning using our proprietary technology, so our low voltage electromagnetic inspection system. So just a brief overview. So I'll briefly go through, or I'll actually go through the technology in some detail, and then we'll get into two different case studies. One that we'll actually be presenting at the short course in detail, but I'm just going to show you a couple wells from that case study that we did with an operator in California, so achieving longer run times, and then a case study on altering rod designs based on some of the indications we were seeing on the EMI scans with an operator in the Permian Basin. And then we'll get into some future work and conclusions. Before I do get into the technology, I do want to just mention, if you have any questions, I forgot to mention this at the very beginning, just enter them into the question box and we will address all the questions at the end. Okay, so getting into the low voltage EMI technology. So I'm sure, as most of you are familiar, electromagnetic testing is a form of non-destructive testing involving the induction of either electric currents, magnetic fields, or a combination of both. And so when a test is executed properly, a defect inside of the test object will generate a detectable response. So our unit is compact in design, as you can see here. And so it allows for placement between the last guide arm and the collapsible service reel when you are pulling continuous rod. So our unit is comprised of two components that basically clamp on around the rod, allowing it to be easily installed or removed at any time during operation. And we designed it to meet a class 1 Div 2 rating. So it makes it suitable to be used near the wellhead, and it uses magnets to induce magnetic fields for the object testing. So this ring that you see here induces the magnetic field, and this configuration enables accurate inspection of continuous rod while also adhering to safety standards. So just a little bit about the operations. So when we're scanning a continuous rod string, the rod will travel through the injector before entering the guide arms. And prior to entering the guide arms, we have rubber strippers that we use to eliminate excess oil and paraffin on the rod string. And that ensures that the scan occurs with optimal conditions. So we're mitigating, any potential data interference. The rod will then travel through the guide arms, an additional set of rubber strippers before entering the EMI unit and then the collapsible service reel where it continues to spool. So just a little bit more about the unit. So our unit measures magnetic flux leakage and magnetic flux density. So magnetic flux leakage, or MFL, will detect your corrosion pitting or three-dimensional discontinuities. And then magnetic flux density will detect your cross-sectional loss, your wear, changes in permeability of the rod string. So it'd be able to detect a weld, which is, something you see in continuous rod a lot. And so this picture, this image you see here is actually what the EMI operator is seeing as the rod string is traveling through the unit. So top portion here is measuring our magnetic flux leakage, and then the bottom portion here is measuring the magnetic flux density. So a bit more about the unit. So the unit detects variations in the magnetic field with the magnets installed in the housing, material imperfections, as well as relative motion between the rod string and the apparatus while scanning the rod out of the wellbore may both result in those variations. And so variations caused by imperfections are defined as signals, while variations caused by relative motion are defined as noise. And so we want to be able to eliminate that signal noise resulting from the relative movement between the string and the sensors. And so to do that, we added an accelerometer to the unit. And that accelerometer is this blue line that you see right here. So the unit graphs the signals from the accelerometer to monitor for noise created by an impact or movement. And so in this particular case, we have an accelerometer signal that coincides, here with an EMI signal. A few other things about the unit. So speed is controlled by the operator. So I'm sure if you're familiar with EMI, you probably know this, but the slower you run the rod through the EMI unit, the harder it is to read the magnetic field that's generated from the sensors. So it limits the amplification required to see the spikes on the graph. The faster you run the rod through the scanning unit from the Hall effect and the surge coils, it results in magnified peaks from the discontinuities in the rod string. So we can then adjust this amplification to adjust for variations in the speed. So basically, in simple terms, the peaks seen on the graph are more pronounced when you're running faster, and the discontinuities are the same, but under slower speeds cannot be seen underneath the graphs or on the graphs. Typical EMI units are measured in milliseconds, recorded, stored, and converted into the signals that you see on the graphs. So think of an EKG. The signals are seen in the same way, only with different measurements and sensors. Contact versus non-contact. So much in the same way that speed affects the signal magnification on the graph, contact versus contactless have a similar effect. So the further that the sensor is away from the object being scanned, the signal diminishes. And so this, coupled with speed, oftentimes results in inaccurate readings. And so when sensors are in contact with the object, the signals are at their highest level of sensing capability. However, when using contact sensors, the surface of the alloy must be relatively clean to prevent paraffin and oil buildup. And so contact with controlled speed best emulates plant environment conditions when you're scanning continuous rod at the well site. Calibration, we calibrate before every job with coupons. So we've made to ensure that the unit is ready for inspection when we go to scan your continuous rod string. One other thing that I just wanted to mention is we're adapting this technology for coil tubing, which we'll discuss at the end, as well as production tubing, but we can scan 4 inches within an upset, which is different than the traditional EMI unit. So before we get into one of the case studies, I really want to discuss rod fatigue because it's very applicable to the case study that we'll be discussing. And so this was a common indication that we were observing initially when we started using this technology, but didn't quite have a name for it. So through our EMI scans, we found these fluctuations observed near areas where the rod string would part. And the fluctuations are detected are associated with hardness variations in the rod string. So kind of how I mentioned earlier a few slides ago, we can detect the changes in the permeability of the rod string. And these variations can alter the magnetic permeability properties of the rod string, contributing to, fatigue. So the fluctuations are results from repetitive stretching and compression that the rod undergoes over time during its operational cycles. So it's similar to bending a paperclip over and over again until it breaks. And the severity of these fluctuations varies depending on factors such as, how fast the operator is running the unit at and the degree of deviation in the operational condition. So, maybe how severe the deviation is, but also if there's a multitude of severe deviations, that's kind of where we see a lot of the problems. As far as reporting goes for rod fatigue, the density of these fluctuations and the length of the fluctuation section play really crucial roles in how the EMI operator interprets the severity of the issue. And so this guides how the input of the data into the report that you'll see or the end user will see, and it'll provide you with a comprehensive understanding of the condition of the rod string. So here you can see some moderate fluctuations. So this is some rod fatigue that we're seeing. So it's a different indication than, a cross-sectional loss, and a weld also looks different than this. So I'm going to explain the thresholds and our reporting system, and then we'll get in so you can understand the case studies. So continuous rod is not API. And so to come up with our thresholds of what we recommend our customers remove when we're scanning these rod strings, we loosely based it on API 11BR. So you can see that on the left here. So any crack shall be cause for rejection. Mechanical damage that leaves sharp indications on the rod body are rejected. Loss of cross-sectional area due to corrosion, wear, defects, so those three-dimensional discontinuities greater than 20 thousandths would be downgraded to a class 2 rod or rejected. And then wear between 20 to 30% reduction in cross-sectional area or corrosion pits of 40 to 60 thousandths are rejected or downgraded to a class 3 rod. So based on this, we've come to these thresholds here. So our magnetic flux leakage indications, so again, corrosion pitting, three-dimensional discontinuities, we recommend removing 6%, greater than 6% of the rod diameter. So that percentage is based on, the rod diameter. And then magnetic flux density indications recommend removing greater than 15% cross-sectional area or loss. So after that scan is complete, so those screenshots that you saw what the EMI operator was seeing, he'll input those findings into a profile report. So it's very similar to a tubing scan report, as you can see. And the findings are from screenshots, taken during the operation. And each screenshot in this case, in this particular instance, represents an average of about a 50-foot section in the rod string. And so each inspection screenshot is captured about every 30 seconds or so, depending on the speed at which the rod string is pulled. So this average section can vary slightly just depending on how fast they're pulling that rod string. For the magnetic flux leakage, this is on the left here. This black line here represents 6%. So we clearly recommend replacing this section here. It's well above that threshold. And there's a significant, significant length of section that has those indications. And then magnetic flux density is on the right here. This line is 15%. So this is some, moderate wear, and there'll be comments as well on the right, as you see. So this was a semi-elliptical rod string we scanned. So you have wear on minor, scale, and then again, we do pick up welds. So transition weld, or maybe this could have been just a splice weld here. And then we'll also have a summary page. So blue here represents magnetic flux leakage. Red represents magnetic flux density, and it's just kind of like a quick summary. And you have your footage of your rod string here. And then this graph here is your max indication per section. So just the highest indication in that section of your rod string. So, and then there'll be comments, so pitting, MFD fluctuations. And then we'll also input pictures into the report of some of the indications that you do see as well. So now that you guys have an understanding of the reporting, I'm going to go into the first case study. So this is just a couple wells from a case study that we're going to be presenting in April at the short course. And there'll be more wells that we present on at the short course, but just wanted to give a little quick preview of it. So for this operator, they utilize continuous rod to address challenges of loading conditions at deep pump depths with high fluid rates, along with casing restrictions. So mainly using long stroke units, and with continuous rod, you have the advantage of running 1 1/8 continuous rod in a smaller tubing size, so 2 7/8 tubing. You wouldn't be able to do that with conventional stick rod, and therefore you can make more fluid with continuous rod. And they have a widespread continuous rod population, and a lot of these strings are older than 10 years. And so they've scanned a lot of rod strings with us over the last 2 years, over 115 rod strings. And with that information so far, their criteria has come to the following. So they scan any high failure rate wells. So any wells that meet their, whatever their standard is for high failure rate. And then any well that is a cause related scan. So basically any wells that the cause of failure is related to the rod string, they'll also scan the rod string at that time. So on these next 4 slides, you're going to see 2 magnetic flux leakage graphs and 2 magnetic flux density graphs for 2 separate rod strings on 2 different wells. And so here, the y-axis is your defect severity in terms of percentage, and then we have the footage of the rod string on the x-axis. Yellow, so in this first one, we're looking at magnetic flux leakage, which is, corrosion pitting again, and three-dimensional discontinuities. And then, so yellow is up to about 6%, and then blue will go up to 14, and anything past that is red. So that's kind of how the color coding works. And on this particular well, it was installed in May of 2019, and the operator pulled it in on November 6, 2023 for elective well work. And the crew noted that the rod string had light pitting and wear, but it was fine to run back in. And after running for only 1 week after the elective well work, the operator had a rod failure. And at that time, they decided to EMI the rod string and came to the conclusion based on the EMI scan that there was severe pitting in the top 650 feet of the rod string. And you'll see on the next slide, but also had some moderate wear on the bottom. So you can see a picture here of the pitting on the top portion of the rod string. So this is the magnetic flux density graph or indications for this particular well. And you can see some, just some moderate wear towards the bottom. And so with the scan, the operator ended up replacing the top 650 feet or so, and it's now been running since they replaced it back in November. But had they been able to maybe scan it when they were doing the elective well work, they likely could have prevented a repeat rod failure that they ended up seeing with this on this particular rod string. Well number 2. So this co-rod parted at 950 feet. Both of these wells, semi-elliptical rod strings, should have mentioned that at the beginning, but this was in the number 6 taper. And at the time of failure, you can see here, so it is a older rod string installed in April of 2013. And at the time of failure, when it did part at 950 feet, the crew noted light pitting, but only needed to cut and replace about 60 feet above and below the failure, and that the remainder of the rod string was in good condition and could be rerun back in the well bore. The well ended up failing for another rod part just a little over 2 months later, and so the operator decided to EMI the rod string at this time. And the failure was actually near the transition between the 6 and 7 taper. But as you can see by the EMI results, the rod string was highly compromised throughout. So in this case, this is magnetic flux leakage. So again, corrosion pitting, three-dimensional discontinuities. And in this case, these indications were representative of pitting throughout the rod string. And they also had, pretty moderate to severe wear in the top about half of the rod string. And so at this time, it was, installed in April of 2013, and they decided to retire the rod string at this time. And so these 2 wells are just a good example of how scanning continuous rod during a workover can help prevent repeat rod failures. Maybe had they scanned it at the initial, could have prevented the second failure by removing that 650 feet initially, or replacing this rod string at the prior time where they pulled it in August of 2013. Excuse me. Okay, so getting into the next case study here. So this one is based on altering rod design. So this was done in the Permian Basin with another operator. And I'm going to give you a little brief summary of kind of what happened on this well. There's a lot of moving parts, but as I go through the study, it'll help and it'll be probably easier to follow. So we initially installed a new rod string with this operator in December of 2021, consisting of a 8/7/8 taper, so a 1-inch, 7/8, 1-inch. This is round continuous rod. They had an 1 3/4 tubing pump because they were using some 2 7/8 line tubing in a couple spots, couple problematic areas. It was making around 300 barrels of fluid per day, and at a stroke, I think they were running around 6 strokes per minute. And then it ran for only 70 days. And in March of 2022, they had to pull the rod string due to a part at 2860 in the 7/8 inch section. And so at this time, based on the scan, which you're going to see on the next 2 slides, We recommended replacing 500 feet in the 7/8 inch section. So it's about 400 feet above the part and then 100 feet beneath the part based on the scan. And so we reran the string, but for some reason there happened to be a miscommunication in the field and only 400 feet was cut out. So the 100 feet beneath the part was not removed. And so they reran the string back in with that 400 foot new section, and the rod string parted again 20 days later. And about 20 feet beneath the original part. So first failure was at 2860, as you can see here. And then the second failure was at 2880. So really close. And so in May, based on the two failures and the severity of the MFD indications, which you'll see in a couple slides after really short run times, we did recommend running a gyro. And so I'm going to show you the gyro and the MWD overlaid, as well as the gyro with the MFD indications for the March and the May scans. And then we'll get to the new string that we designed and the new run times. So this is the March MFL scan. So magnetic flux leakage. We're looking at three-dimensional discontinuities, corrosion pitting. We have the percentage of the indication here, and then the footage of the rod string. And so you can see this is after about a 70-day runtime. We have our failure location right here, and there was some corrosion pitting right above the failure. And then for our magnetic flux density, you can see we have pretty significant indications for a 70-day runtime. And so there was some MFD fluctuations right above the rod part, and you can't actually scan the rod part, but you can see there was some MFD fluctuations right above the part. Failure location right here also had some rod wear at the bottom of the rod string. And, this was, after a really short runtime. And so again, based on the scan, we recommended cutting out 500 feet, but there was a miscommunication and 400 feet was replaced. And so that rod part was found, 20 feet beneath the initial part. So in the May scan, we went ahead and scanned the rod string again. It looked pretty similar to what you see here. There was a few more indications on the bottom, which you'll see when I overlay it with the gyro. But we did also send the rod failures off, and the root cause of failure was basically shown to be from compression buckling, and we can attribute that to pushing through severe deviation. And so we did recommend running a gyro. So this here is the gyro overlaid with the MWD. So this gyro is a 25-foot interval intubing gyro. The left here is dogleg severity. Right here is our side loading. The orange is the gyro. Blue is the MWD. And you can see, the MWD, it's a little bit harder to see since it's underneath, but the average throughout was about 1 degree beneath 2,500 feet. You can see the deviation was significantly worse. There, you do have some significant deviation directly above the pump, and as well as the shallow deviation when you're making, you're above between 3 to 4 degrees. And when you're making, 300 barrels of fluid per day at close to 7 strokes per minute, it is difficult to push through that deviation on rod pumps successfully. And so that's why we were seeing such severe MFD fluctuations after such a short runtime. So this here's the March scan. So the March blue scan, the blue indicates our MFD indications. The orange is the gyro. And so the left axis here is our dogleg severity. So this is what the orange is based on. And then the right here is our MFT indication and percentage, our MFD fluctuations. And so that's what the blue is based on here. We have the footage of the rod string and our failure location right here. So you can see, the dogleg severity along with the MFD fluctuations. Again, we have those MFD fluctuations directly above the part, which is what, how we came to determine what this rod fatigue was. And then this is our May scan with our MFD indications. You'll notice you don't have any MFD fluctuations right above the part where we were seeing it, and that's because we just replaced that rod string with new rod. And so that's why we don't see it on this particular scan. There is a few more indications down low after running for 20 more days. And so based on, these MFD fluctuations we were seeing, and then they ended up running the gyro, we found that one of the best ways, and we've done this in quite a few other wells in the Permian Basin, one of the best ways to push through wells with, pretty significant dog legs, but it's not necessarily how significant those dog legs are, but it's also how many deviations there are. So like the multitude of deviations that you saw throughout the entire wellbore is to beef up the rod string. And so we ended up running in a 9/8/7/8 taper. And so in that top section where we were seeing such, significant fluctuations, we ran in 1/8 and 1-inch rod in the most severe deviated spots. And about everything else was kept the same. So after an initial runtime of 70 days, this rod string now has been running for about 630 days, over 630 days. So we'll be coming up in May of 2 years. So it's really been a good success story of how applying these EMI scans to help alter the rod strings based on the fluctuations, from a multitude of deviations has helped increase run times. So our current and our future work. So currently, we've commercialized this unit, scanning for over 2 years on both round and semi-elliptical continuous rod. And we have documented case studies. Again, we'll be presenting in April at the short course on that first case study that I showed you a couple wells on. And then in 2024, to be commercialized, we plan to roll out our new Zephyr software and data logger at the end of Q1 of this quarter. We're adapting the unit for coiled tubing in the second half of this year. So it's going to be, a similar method or operation to continuous rod. And then lastly, we do plan to begin prototyping for rack mounted tubing scanning at the well site with this technology and software and data logger as well. And so conclusion, so based on this presentation today and the 2 case studies I presented, because a historical challenge to widespread adoption of continuous rod is repeat rod failures, we can come to the following conclusions: that this EMI unit allows operators to detect and address issues such as corrosion, wear, fatigue. It allows operators to alter operations in wellbores such as, chemical programs, allows operators to alter your rod designs based on the type of indication that you're seeing, so like the MFD fluctuations. And the integration of the technology alongside visual inspections leads to proactive maintenance and reduced repeat rod failures, helping, increase, helping you with substantial cost savings. And so that's all I had today. Again, we really appreciate your time, and we'll go ahead and open it up for questions for Q&A. So if you have any questions, just put it in the chat. Okay, Inyo, I do have a question for you.
Yes.
Okay, so how do we calibrate the unit?
The unit get calibrated by a standard we have, but we also use a pulsar to read the response from the sensors and set the node at the same level before we run it.
Okay. Thank you. And then LJ, are we able to scan stick rod?
No, we're not able to scan stick rod at this time due to the upsets with the couplings. We don't have an effective way to ride over the couplings. We can scan in between the couplings, but that's not economically feasible. So until we develop a method to ride over the couplings, we we cannot scan continuous conventional stick rod.
Okay, thank you. Enio, what is the level of detection and flaws that the unit is able to detect?
Same as a conventional unit. Same thing that a conventional unit will pick up with search coils, we can pick it up.
So it's as good or better accuracy with a conventional unit with our unit. Would you say that, Eno?
Yeah, I would say that. Yeah.
And I have a question, for Eno, really. It's a rare question, but can the unit detect iron sulfide?
Uh,
Yeah, the unit doesn't detect iron sulfide per se. The unit detects alterations of the magnetic fields, and you go and look up the indications on the rod. The iron sulfide is a non-magnetic material, so and it presents itself in the form of scales. So it starts like a little beating, and then it starts gradually increasing until it gets to massive scales. Very easy to not very easy. They present itself on this particular color, so you know you're dealing with iron sulfide, and then those scales not being magnetic, it shows on the flux density as a loss of metal. Throughout our experience on over 400 jobs, we have come to 2 strings that had the iron sulfide present, and we do recommend to change because it does make the string prone to failure.
okay, thank you. Do have a question here. I'll take this one. It says for rod design, is the gyro run in casing as useful as gyro run in tubing? And so we do recommend it in tubing. You'll typically see the deviation be different than in casing, but I mean, if you can, a gyro in casing is preferred over you know, a 100-foot interval MWD, because you are going to see typically what we see is we'll see about 1.5 to 2 times the deviation that you'll see in an MWD with the gyro.
But it's more accurate inside of tubing than in casing, which is the question. So you'd always want to prefer, if you have the option, you want to do the gyro on a tubing versus a casing.
Right. And then do a couple more questions here. How is the repeatability or the accuracy of the system?
Eno, you want to take
Oh,
this
that's
one?
me? Yeah,
The
same as
repeatability and accuracy.
it's an EMI unit. It's same as a conventional unit. So pretty much it's a conventional unit. You run the standard 4 times and you picked up all the defects at the very same level, same way as a conventional unit.
So one of the other things to add to that is not only does the operator, when he's detecting the MFL and MFD fluctuations on the graph, when we see that, the operator or one of his hands walk over to the 6-meter reel that is spooling, and we take a picture of it. So if the flaw is significant enough for us to be able to detect it visually with the naked eye, we'll see it and take a picture of that, and then that is coupled with the report that's presented, and it matches with the spike that you're seeing on the screen. So I just wanted to point that out, that we see a visual, we actually see it. So what you cannot see with the eye, we also pick up. But the minimum that we see on the screen, which might be a question that could be asked, would be, you know, what is the level of detection? And it's usually 10 thousandths of an inch or above, our unit or any conventional EMI unit will detect that. Anything below that is very difficult to see, below 10 thousandths of an inch.
Perfect. Thank you. I'll do one last question. LJ, if you want to take this, or I can. What is the max number of sections that you recommend removing before replacing a rod string? So I guess how many sections can you cut and replace when you are, if you're looking at a report? If
And
there's-
you're the better subject matter expert in doing this daily out there, so I'll defer to you of what your recommendations are.
I would say probably no more, I don't want to put a firm number on it, but probably 3 or 4. You don't want to cut and replace just because the added rig time between, removing that section, welding it back, replacing, and then, adding those 2 welds for just 1 section. It's just a lot of extra rig time, and it may just be better off to run a new string, and then the stuff that is in acceptable condition, we can store at our yard and, use for a future rod string. It's probably more beneficial as far as, rig time and cost.
So really you want to, and what you're saying is really want to minimize the amount of field splices and welds in a rod string, in addition to not only the condition of the rod string and cutting out the corrosion or what you might consider the rerun. It really boils down to, you want to minimize the amount of welds that you have in a rod string as possible. Would that be accurate, Ann?
Yeah, that's basically what I'm saying.
I have a few comments, and if there are no other questions, I actually have a few comments I'd like to bring up, but I'll let you finish the questions.
No, that's it.
Okay. One important thing to note on the last case study that Ann presented in this presentation, significant note is the operator, upon that second failure, was really giving us another shot at it based on having several scan reports to help us recommend the right solution for it or design for it. Was moving this well off a rod pump altogether. So we either had one last shot of it after it, and then they were going to move it to some other form of artificial lift. So when you look at that 630 days of runtime, the value of having EMI, that last case study speaks for itself, because this was an operator who was going to take it off of rod pumping, and everything that we're focused on is really the life span of rod pumping in shale oil and gas wells. The other comment you had brought up, 11 API BR, API does not cover continuous sucker rod today, although there is a committee that has been formed to try to get core rod included in 11 API BR. But as of now, it is not, but we do comply with API 11 BR standards. And one other important is with tapered rod strings. Those of you who have a familiarity with tapered rod strings and EMI, you're changing rod sizes. So question might come up is, how do you account for the different rod sizes when you're running an EMI? Because in theory, you should recalibrate for every rod size. That's done electronically and with algorithms that we have custom built into the software and the software side. And that's what accounts for it. We know exactly what that is because it's a 1 inch to 7/8, a 15/16 to 1 inch. So we've modeled that and built algorithms and electronics to handle that. Back to you, Ann.
That's all I had. We're getting pretty short on time here, so there's no more questions. We can, no more comments. We can go ahead and wrap up the webinar. Thank you for joining us today.